Yeah, 3, start now.
Okay, so, yep, take 3. So if you're in 5th period, I would like you to try the warm-up. Have the substitute hit pause on the video, and when you are ready to see the answers, press play. And here are the answers. All right, the measure of an arc is equal to the measure of the central angle. A measure of an inscribed angle is half the intercepted arc, and we also need to keep in mind that a radius, when it is perpendicular to a chord, it not only bisects the chord, but it also bisects the intercepted arc. So the answers are 45, 72 pi, and AF. I'll explain this tomorrow if anybody has any questions. Here are the answers to the homework. You can go ahead and press pause again until everybody's done checking their homework. And when you're ready, please press play.
Play.
All right, I think we're ready. Okay, so for today's lesson, what are we going to look at? We're going to look at some functions that could be classified as piecewise functions. They don't have to be classified as piecewise functions, but they could be. There they are. And what I'm going to do is I'm going to have
I'll pass it out. Oh.
some helpers pass that out.
And we have stats. Yeah.
Legend. Agents of Change.
That's just Stacy.
Okay, so right now we should be passing out today's worksheet. We're going to do some of these problems together, and then you're going to have some to do for homework. Or classwork, hopefully.
Hayden, can I get a sheet? Thanks. Appreciate it.
Okay. So hopefully now the worksheets have been passed out, and everybody has one. Before we get started, let's talk about what an absolute value function is. We know that these symbols mean absolute value, right? Okay. So this is the parent graph for our absolute value function. So everybody's just going to watch for a moment, and then we're going to apply it to the problems we have on our worksheet you just received. Okay. So if I thought about moves for the parent graph, it hasn't been shifted any, so where do you think it's going to start?
0, 0.
0, 0. Now, if we made a table of values, and we started with 0, if we plugged in 0, is the absolute value of 0, 0?
Yes.
Because the absolute value means distance from 0 on the number line. How far away from 0 is 0?
0.
0. Okay? Now, how far away is 1 from 0?
1.
1. How far away is 2 from 0? 2. How far away is negative 1 from 0? 1. How far away is negative 2 from 0? 2. So, we may think in our head the shortcut, absolute value just makes everything positive. But what it is, absolute value is a measure of a distance from 0. And can a measure of a distance ever be negative? No. Okay. So if we were to graph this function, it makes the pretty V we talked about yesterday for a minute. And it is nice and symmetric. The right and left side mirror each other. So since it's symmetric, it has an axis of symmetry. And that's what it looks like. Okay, so that is the parent graph for an absolute value function. Do you guys see two pieces though?
Yeah.
Do you see how I could write it as a piecewise function?
Yes.
This being one piece, this being the second piece. Okay? So, let's talk about domain. Is there any restriction? No. I can plug in any real number and it works. The range of the parent graph is going to be 0 to infinity. Like we said just a moment ago, because it is beautifully symmetric, it does have an axis of symmetry. And for this one, the axis of symmetry is x equals 0. If we were to fold it across the y-axis, it would fold perfectly on top of each other. Okay, increasing, decreasing, where's the function increasing? 0 to infinity. Where is it decreasing?
Negative infinity.
Negative infinity to 0. How about in behavior?
Positive.
Very good. Let's take the shortcut. As x approaches positive or negative infinity, the y approaches positive infinity. Beautiful. Okay. And obviously, it'll either have a max or a min, depending on how it opens. And that max or min occurs at the vertex. So it's going to transform itself just like all the other functions we've studied. So where would this vertex shift to on number 1? 3, 2. Boom. The absolute value of 1 is 1. Negative 1 is 1. The absolute value of 2 is 2. The absolute value of negative 2 is 2. Does that make sense? All right. Boom.
You grabbed that last point.
I may have. 1, 2. 1, 1, 2, 2. Thank you. Okay, fine. All right. And so it says to give the characteristics. So the domain of this one is from negative infinity to positive infinity. The range is what? 2 to infinity. In behavior, just like the parent function. As x approaches positive or negative infinity, y approaches positive infinity. Axis of symmetry, what would the axis of symmetry be on this one? X equals 3. This would have a min. Where would the min occur?
3, 2.
The min would occur at the point 3, 2, or you could say the function has a minimum value of 2. All right, let's skip to 5. Yes, ma'am.
Do you want us to increasing if it decreases?
Yeah, we should. It's increasing from 3 to infinity. It's decreasing from negative infinity to 3. I talked about in behavior, but I didn't write it. There's not enough room. All right, let's look at number 5. What do you think is going to be different about number 5? It's a reflection. So, where's the vertex?
Up 4.
0, 4. Up 4. And instead of opening up, it will open down. All right.
All this was that easy.
We got it?
Yeah.
Okay. So this is going to change our range a wee bit. Because range is always the least y value to the greatest y value.
Negative infinity then 4.
Negative infinity to 4. And I think you can do the rest. Also changes the in behavior. As x approaches positive or negative infinity, y approaches,
Whichever
Negative infinity.
yeah, whichever way it's pointing. In this case, negative infinity. All right, what will the 3 do? Stretch it, that's right. So this one's going to have a vertex over here at positive 4. But instead of 1, 1, we're going 1, 3. So it's a vertically stretched, which results in a more narrow, when we stretch it vertically, a narrow V. Okay, we get the idea? All right, your classwork is to finish up the ones we didn't do. I want you to pick 2 of them and do characteristics on 2.
And then the rest of the sheet is over.
All right? Okay, let's take a look at part 2. Write an absolute value equation and a piecewise function for each graph. Okay. So, they're all V's. And if we look at them, the slope, let's check out the slope. The slope on this side is over 1 up 2. What is the slope on this side? Left 1 up 2. So the slopes are just opposites, aren't they? Okay? The slope, this one looks off.
Yeah.
That one doesn't look perfect.
I said 1.5.
It's not going through.
Let's skip that one. All right, this one, the slope is 1, 1, 1, 1, 1, 1, and this is 1, 1. Okay, so positive 1 and negative 1. So what we'll notice on absolute value functions is those slopes are just opposites. That's what makes them symmetric. Okay, so if we were to write it as an absolute value function, absolute value of, it shifted, how?
Down 6.
Down 6. So that's just going to put a minus 6 at the end. Now, is there any reflection or vertical stretch or compression? It does appear to be 2. Okay, that's it. We wrote the absolute value function. That one's easy. Now, when we look at the other, we have the 2 parts. Okay, so if we wrote it as a piecewise function, f of x equals or y equals, this one has a slope of negative 2 and a y-intercept at negative 6. Okay, and that's for x values that are less or equal to 0. The slope of your second piece will always just be the opposite. So if this was negative 2, this is going to be positive 2. And the y-intercept is negative 6. If x is greater than 0. This one's just off a little. Is it off on yours too?
Yeah.
Let's skip this one since it's off a little.
Alright, thank you.
Okay, get the idea on that? Okay. Now, do you see that this right here is this graph?
What?
I did that on. So this says to solve absolute value equations using their graph. So where does this function equal 0? Who sees it? Right here and right there. Okay, so it's going to equal 0 at positive and negative 3. Now let's see if that makes sense if we were to solve it algebraically. Let's talk about how you solve an absolute value function algebraically. Some of you may remember, some of you may have never seen it. So the first thing we would do was get the absolute value part by itself. Okay, so to do that we would have to move 6 to the other side and divide by 2. Okay, now, positive or negative 3. The absolute value of either of them is 3. Because everything in here can equal positive 3 or everything in here can equal negative 3. So x equals positive or negative 3. Okay, let's look at that same thing in terms of number 8.
I think this is on the PSAT.
It is.
Remember that.
Number 8 is not quite as simple, but it's the same process. So if we were to solve number 8 algebraically, we would try to isolate the x, which means we want to get the absolute value by itself. And the way we do that is we move the 4 over. Divide by 4/3 and multiply by the reciprocal. Negative 3/4. And so we get the absolute value of x equals 3. Okay, so what this means is all of this stuff in here could equal 3, or all of this stuff in here could equal negative 3. Because what is the absolute value of negative 3? 3. So you say x plus 1 equals 3, or x plus 1 equals negative 3. And we solve. So x equals 2, or negative 4. Make sense? Now, what happens if you had an absolute value equal to a negative number? Nothing. It can't happen. What do we write when there's nothing? No solution. There'd be no solution. Very good. Now this one, if we were asked to sketch a graph and solve an inequality, let me steal this real quick and put it on a new page. New. How could we do that? So when I leave, you guys are going to have to put thinking caps on and see together if you can determine how to solve some of these. Some of these are going to make you think. That's right.
We can telecommunicate.
We're going to do the first one together, and then you'll have to put your thinking caps on for the rest of it. If we are to solve this graphically, so we have a shift left 1, down 4, right? And then we would, I totally messed up. Let's see, where's my line tool? Okay, graphically it's pretty simple. Where is it less than or equal to 0? Isn't the function negative down here?
Yes.
So, graphically it's pretty easy to see from this x value to this x value, this function is less than or equal to 0. Can you see that on the graph? It is below the x-axis. So what would that interval be? From -5 to +3. Okay? Okay, so that's how we would solve it algebraically. Now what if this number was not 0? What if it was something like -1? We would just come down here and we would think about, okay, where would it be less than or equal to -1? And I would draw in a line down here at hold on. I would draw a line in at -1 and look at what are those x values? What's the x value here and what's the x value there? That's where the function is less than, down there. So it would shift my interval a little bit. Now what if it had said greater than instead of less than? If it had said greater than, I'd be looking at this part and this part. So had it said greater than or equal to 0, that would mix things up a little bit. My answer would look like this. It would go from -infinity to what was this x value? -5. Union with, ooh, I said equal to, so I need to be inclusive. And then it would be 3 to infinity. Okay, your homework is on the board, but I'm going to write it here also. So you're to complete the front of the worksheet.
This right here.
Yes. Okay, also, we have bookwork, and you may use your technology to look this up. We are just doing 1 through 10 on page 413. Now, some of these are thinker questions. I love them. Always, sometimes, never. Okay? So, be ready tomorrow to defend your answers. So, if you think it's sometimes, if I call on you tomorrow, be ready to explain why you think it's sometimes. Okay? All right.
Do we have a song for this class?
No, do my